In the second lecture on aircraft structures, we will look at the concept of a beam. What is a beam and how is a beam related to a truss structure? Remember, a truss structure was often used in the early years of aviation. Let's first repeat a few ideas from previous lecture. In the first lecture, we looked at the concept of structure and we elaborated on the functions of structures in general and of aircraft structures in particular. These functions are load transfer, protection, and provision of attachment points. We should realize that in a structure consists of many elements. Many elements are, as I call them, beam-like elements. In the figure, we see a so-called I-beam. This is a structural element you can see in many structures. Think, for example, about buildings and bridges. This I-beam has three features: an upper flange, a lower flange, and a web plate between the flanges. The I-beam is just one example of a beam-like element. In aircraft structures, you may discover many of these elements. Other examples are Z-beams or Z-profiles, C-beams, and head stiffeners. All these beams or profiles can be characterized by the same features as an I-beam. They have flanges at top and bottom and one or two web plates between these flanges. Later I will come back to these features. Let's first go back to trusses. In the previous lecture we have seen that in the early days of aviation, truss structures were used. Those structures were easy to manufacture, elegant, and had a low weight. A truss structure can also be regarded as a beam-like element. I will explain that in this lecture. The first two figures show a simple truss element. It consists of three bars which are connected to the floor. The joints are hinges which allow rotation, as can be seen in the second figure. In this figure, a load is applied to the right and the truss easily rotates. In other words, it cannot resist the load. It cannot carry the load. If we replace the hinges by welded joints, we get rigid joints. If we now apply the same load, the truss is able to carry this load. However, the truss also deforms. A much more elegant solution is when we insert two wires or a bar element in the truss. On the left-hand side, we see the option with two wires. Two wires because wires can only carry tension loads, but no compression loads. In the right-hand figure, we inserted one bar, which can carry tension and compression loads. Both trusses are now stable and can resist the horizontal loads. The last figure on the previous slide showed a truss with one diagonal bar. What happens if we insert two diagonal bars? In the first place, it will be rather difficult to insert the second bar. Only when it fits very accurately, it is possible. In the second place, calculation of forces in the truss will become more difficult. This is because of the residual stresses which are introduced in a truss when the second bar is inserted. But the two diagonals also provide an advantage. The truss has become fail-safe. In other words, if one of the element fails, the truss is still able to carry the load. Let's compare the two concepts. A truss with one diagonal bar and a truss with two diagonal bars. The concept with one diagonal bar has just enough bars to carry the loads. If we remove one bar, the truss will collapse. During the service life of this truss, we cannot afford any failure, so the bars should be strong enough to last till the end. If we look at a truss with two diagonal bars, one bar could fail and the truss will not collapse. The other bars take over the loads of the failed one. During the service life of this truss, failure may occur. However, we have to inspect the truss frequently to see if an element has failed. And if an element has failed, we should replace it. So far we looked at one simple truss, one cell. A larger truss structure may consist of multiple cells, as can be seen in this picture. In this picture we see a combination of bars and wires. The horizontal and vertical elements are bars. The diagonal elements are wires. We suppose that the truss structure is attached to the wall on the left, and when we apply a load F at the truss, this load should be transferred to the supports at the wall. The vertical force is in this case transferred by some of the wires and some of the vertical bars. The vertical force also induces a bending moment, and this moment is carried by the upper and lower horizontal bars. The upper horizontal bars are in tension. The lower horizontal bars are in compression. As you can see in the figure, the cross-section of the bars increase from right to left, because the bending moment in the structure also increases from right to left. Let me remind you that the bending moment equals force times the length of the arm or distance. In this figure, we can see the truss structure in equilibrium. The vertical force is countered by the forces from the support. The bending moment is compensated by opposing bending moments. Also, the horizontal forces are in equilibrium. In this truss, the elements like the bars and the wires connect the location where the load is applied to the support of the structure. That is what we call a load path. From this truss to a beam-like element is a very small step. In this figure, the wires are replaced by a metal plate. The sheet has the same function as the wires. The sheet transfers the vertical loads. The wires were loaded in tension, but the metal sheet is loaded in shear, a combination of tension and compression. If we now look at the overall picture, we can state that the upper and lower bars can take the tension and compression forces resulting from the bending moment. The metal sheet takes care of the vertical or transverse load. An I-beam will do the same. The flanges will take the horizontal loads induced by the bending moment, and the web plates will carry the vertical load. A truss structure with metal sheet acts just like a beam-like element. When a metal sheet is loaded in shear, it may buckle. I can demonstrate this with this structure, a simple wooden frame covered by a sheet of paper. When I bend this beam, the paper will buckle. When I unload the beam, all buckles will disappear. The orientation of the buckles depends on the direction of the loads. And, as with the paper, as long as the buckles are elastic, they will disappear when the beam is unloaded. If the load has become too high, the buckles will become plastic, and they will not disappear when the load is removed. Actually, our structure has failed. To summarize, in this lecture I explained the principle of a truss structure, the differences between safe life and fail-safe, and showed the commonality between a truss and a beam structure.